In this video, we continue to look at problem solving related to stoichiometry and chemical formulas and chemical equations. This is a continuation of chapter 3. But before we get started, we're going to think about problem solving and some strategies that will hopefully be useful to us throughout the semester. We start off with our periodic table. As we said last time, you should have a copy of the periodic table near your computer or wherever it is that you're doing your work. You're going to need a table or workspace where you can work out problems. These are not things that you can simply do from your head and calculate things right on the computer. You're going to need scratch paper and you're going to need a periodic table with you. And that leads us to problem solving strategies. Of course, this is an online course, and that's a little bit more challenging in that we're not together and we can't look at how to work out problems together. So we need to think about this a little bit more intentionally. And these are some things to consider whenever you're doing problem solving. And this is going to become really important when you get to chapters 5 and 6 in particular, but also chapter 4. Because it turns out many of the problems that we're going to do in this course are multi-step problems. They're not just one-step problems. And in fact, that's probably generally true if you're going to be working in lab or you're doing research or chemical bench work in the future. So you don't simply take data, throw it into an equation, and out pops a single result. That's usually not the case. You're usually going to be calculating multiple things, combining them in multiple ways, and doing multiple steps to get to the end point. And in order to do that, you're going to need scratch paper. So you're going to want to have plenty of scratch paper around available on which you can work out problems. And you're going to want to have space to do that. And whenever you're doing multi-step problems, you should practice a number of the problems. And you're going to want to develop a strategy that is kind of best for you. There's not necessarily a unique way to solve each problem. There'll be mathematically equivalent, a variety of ways that are mathematically equivalent and will get you to the correct answer. You just need to find one with which you're comfortable with and which you can use regularly. But all the steps, regardless of the approach that you take, it's going to include the following. You need to figure out where you're starting, what is the end point you're getting to, and you want to build a little flow chart or at least diagram out a flow of all the steps that you're going to need to solve your problem. Whenever you're doing these calculations, you're going to want to make sure that the first thing you do is you balance the chemical reaction for the process that you're looking at. And you're very likely going to need to calculate molar masses, amounts or moles of materials, and sometimes you'll convert to grams, and you're going to want to convert names and formulas. One thing that's sometimes helpful if you're struggling to solve a problem is to do a lot of these basic calculations to begin with and see what information you have and see if that helps you figuring your journey getting to your solution. And finally, of course, when you get to your answer, make sure that you've got units, proper rounding, and proper significant figures in all of your final answers. So let's take an example problem. And this requires us to do kind of a variety of calculations. It's a complex problem because there's multiple steps to it, but it's probably not as complex as some of the things we'll have later in the semester. So let's read the problem. We consider a reaction of diphosphorus pentoxide with water to produce a single product, phosphoric acid. If 1.5 grams of our diphosphorus pentoxide reacts with 1 gram of water, how much phosphoric acid can be produced? So when we look at this and we think, what's involved here? Well, of course, we're going to need to have a variety of things. We need to have a balanced chemical equation here. And the first sentence tells us how to get it there. It tells us that our reactants are P2O5 and water, and our product is a single product, H3PO4. We've got masses, and so we're going to want to convert those to moles. And on the way there, we'll need to have molar masses for diphosphorus pentoxide, water, and phosphoric acid. We're going to want to figure, is there a limiting reagent here? And if so, then can we convert that limiting reagent into a theoretical yield? So let's go through and do this. We start off with our balanced chemical reaction. 1 mole of P2O5 reacts with 3 moles of water plus 2 moles of phosphoric acid. So you would have written down those reactants and products, and you would manually balance that yourself. Once we know this, of course, what are we going to do next? Well, we're going to need molar masses for everything. And the molar masses were calculated here. You guys learned how to do that earlier in this chapter and a little bit at the end of chapter 2, so you should be familiar with these. So these are all of our molecular weights or molar masses. And now we can take our masses up above in the problem and convert them over into moles. So we take our 1.5 grams of P2O5, divide by the molar mass, and that gives us moles of P2O5. So that's how you do that calculation. We end up with moles of water as well. So we know how to do that. We take our 1 gram divided by 18 grams per mole, and we get 0.0555. Now, we know we have 1 mole of P2O5 reacts with 3 moles of H2O. In this case, we have 0.01 moles of P2O5 and 0.05 moles of H2O. So how do we compare those? Well, let's write out ratios like we did last time. The theoretical ratio in our reaction is 1 mole of P2O5 to 3 moles of H2O. The actual ratio is given here. If we divide 0.1057 by 0.0555, we get 0.19. And that is less than 1 over 3, or 0.33. So that tells us the numerator is the limiting reagent, that is, the P2O5. So P2O5 is now our limiting reagent. That's going to dictate to us how much product we get. So let's move on to our next slide. From a reaction, 1 P2O5 produces 2 phosphoric acids. So 0.01057 moles of P2O5 will give us twice as many moles of phosphoric acid, that is 0.211. Now, once we know the moles of phosphoric acid, we can easily convert that into a mass because we had calculated our molar mass of sulfuric acid earlier. We multiply this out and we get 2.07 grams of H3PO4. Now, we're almost finished here, but we have to remember that we should only have 2 significant figures. Turns out we had some calculations earlier and our masses had 2 significant figures on them. And so our answer will be 2.1 grams of phosphoric acid. That's illustrating all these ideas. We've looked at our situation, figured out where we wanted to start and finish, developed a flow plan for it, calculated our basic numbers, and worked them through the problem. Now we're going to look at some just a couple of problems from Silverberg and Amateus. This illustrates a little bit about how the book expresses things, and we'll kind of maybe think about ways that we could improve on this. So our first problem is something we went through last time, figuring out empirical formulas, but in this case it's from masses of elements. So the problem states, analysis of a sample of an ionic compound yields 2.82 grams of sodium, 4.35 grams of chlorine, and 7.83 grams of oxygen. What is the empirical formula and the name of the compound? So we have 2 things to do. We need to figure out the formula and the name. Once we have the formula, that should be straightforward to get the name. So what are the things we're going to need to do? Well, we've got masses, and ultimately we'll want an empirical formula. So from masses, we'll need to get moles. And then once we've got moles, we'll need to come up with the lowest whole number ratios to get the empirical formula. And the plan written down here by Silverberg looks quite reasonable. Find the relative number of moles, divide by the lowest mole amount, and find the relative ratios. So here's their solution. Each of the masses is divided by the atomic mass of the corresponding element. So 2.82 grams of sodium is divided by 22.99, and likewise for chlorine and oxygen. So we end up with, for our sample, these amounts of moles: 0.123 moles of sodium, 0.123 moles of chlorine, and 0.489 moles of oxygen. If we divide all three of those numbers by 0.123, we end up with 1 mole of sodium, 1 mole of chlorine, to 3.98 moles of oxygen. So that gives us an empirical formula of, rounding to whole numbers, NaClO4. And we recognize ClO4 as one of our polyoxoanions, and so it's ClO4 is perchlorate. Sodium, of course, is group 1, so we don't need a number on that, so we don't need to indicate the oxidation state. It's always +1, so we have sodium perchlorate. So that's the solution to that problem. Now, the last problem we're going to look at is a limiting reagent problem. So our problem states the following. It says, a fuel mixture used in the early days of rocketry consisted of two liquids: hydrazine, which is N2H4, and we would name that with the IUPAC name dinitrogen tetrahydride, but we'll just call it hydrazine during this problem because that's the common name, like dihydrogen monoxide's water. And the other is dinitrogen tetroxide, which ignite on contact to form nitrogen gas and water vapor. So this tells us what our reaction is going to be. We know our reactants, hydrazine and dinitrogen tetroxide, and we know our products, N2 and water. By the way, this is what's called a hypergolic fuel, and it's fairly rare. It's fairly rare to find something where you mix two substances together and they spontaneously ignite. And of course, these are two fairly nasty substances, but it's a very useful reaction, producing gas and giving you propulsion. So from our problem in part A, we're told how many grams of nitrogen gas form when 1 times 10 to the 2 grams of hydrazine and 2 times 10 to the 2 grams of dinitrogen tetroxide are mixed. So that's our first part of the problem. And then Silverberg asked us to write a reaction table for this process. So let's look at the plan that text lays out. It says find the limiting reactant by calculating the amount of product that you can form from each given mass of reactant. Make sure you calculate the mass of the same product for each given amount of reactant. Use this information to construct a table. And that's a very, very short overview of what we need to do, because we're going to need to do a series of things. Think for a moment what you would do with this problem. Maybe first thing might be write out a balanced chemical reaction, right? So we'll need to do that. And the next thing is we'll need to convert our masses into moles, because we'll want to compare them with our reaction. And we'll figure out a limiting reagent. And there's a couple of different ways to do that. We'll see how we'll kind of follow the approach that Silverberg has. And then we'll figure out how much product we'll get from this. And once we have that, then we can look at their reaction table. So here's the roadmap. And of course, the roadmap is nice. It has masses converted into amounts, and amounts of each converted into amounts of product. And then from that we figure the mass of the N2. But of course, this is missing a few things. You're going to have to, you're not going to be given the molar masses of these compounds. You have to calculate those. And you also, it's not listed here where the balanced chemical equation is. So that's probably the first thing we'll do. So let's look at how the solution plays out. Of course, at the top, we do have what we need, which is the reaction of hydrazine plus dinitrogen tetroxide goes to nitrogen plus water. So we have 2 moles of the hydrazine, 1 mole of the dinitrogen tetroxide gives 3 moles of nitrogen and 4 moles of H2O. And I think you could probably balance that now that you know how to balance chemical equations. So once we know that, then we can take our masses of each. So if we look first at our hydrazine, we had 100 grams. That says 1.00 times 102. That should be 10 to the 2 power. That's a little glitch in the PowerPoint, but it's 100 grams of N2H4, and we divide that by our molar mass, which we would have calculated, and that gives us moles of hydrazine. And then we can take the moles of hydrazine, and we know that 2 moles of hydrazine give us 3 moles of N2. So we multiply by 3 halves, and that gives us 4.68 moles of N2 produced if we have 100 grams of hydrazine. For the dinitrogen tetroxide, we have 200. That's 2 times 10 to that should be the power 2, not times 102. And we take that and we divide by the molar mass, which you would need to have calculated for dinitrogen tetroxide. You get moles of N2O4. We know from our reaction stoichiometry, we get 3 moles of N2 per mole of N2O4. Therefore, we would get 6 moles of nitrogen. Now, if we look at this and see this approach to the problem, N2H4 will produce less nitrogen than would dinitrogen tetroxide under these conditions. Therefore, N2H4, or hydrazine, is the limiting reagent. And that tells us that whatever we get from that material is what we can get from our reaction, which would be 4.68 moles. And if we take that many moles, multiply by the molar mass of nitrogen gas, which exists as N2, then we get our product amount, 131 grams of N2. And this has 3 significant figures because our masses have 3 significant figures. So our last problem, Here's our reaction table. The reaction table shows us amounts of reactant and product before the reaction starts, on the bottom line after the reaction happens, and it shows us the change that occurs. So here's our last problem. And this is written out here as silicon carbide is made by reacting sand with powdered carbon at high temperature. Carbon monoxide is also formed. What is the percent yield if 51.4 kilograms of silicon carbide is recovered from processing 100 kilograms of sand? So that's your problem. Now, before we look at Silverberg's roadmap or solution, let's think about the things that we might want to do ourselves. First off, we want to write out a chemical reaction, right? So silicon carbide is made, silicon carbide is a product, by reacting sand, so silicon dioxide is a reactant, with powdered carbon, so that's elemental carbon, that's C, that's a reactant. Carbon monoxide is also formed, so that's a product. So our reaction is going to look like SiO2 plus C yields SiC plus CO. And then we'd want to balance that equation. And then we're told what percent yield will we have if we have 51.4 kilograms of silicon carbide recovered from processing 100 kilograms of sand. This problem, the way it is written, assumes that you must have excess carbon as a reactant, and so the silicon dioxide will be the limiting reagent. So based on that, then we're going to convert those masses for silicon carbide and silicon dioxide into moles, and we'll do an appropriate comparison. So let's look at the plan that is laid out by Silverberg. And they start off quite well. After writing the balanced equation, we convert the given mass of silicon dioxide to an amount. We use the molar ratio to find the amount of silicon carbide and convert it to a mass to obtain the theoretical yield. And that looks very good. And you can see a roadmap next to it. The reaction, writing out a balanced reaction and calculating molar masses is put onto the roadmap. Well, let's look at it. So here we got SiO2 plus 3C gives SiC plus 2CO. Silicon dioxide plus 3 moles of carbon gives 1 mole of silicon carbide and 2 moles of carbon monoxide. That is our balanced chemical equation. It also tells us that 1 mole of SiO2 gives 1 mole of SiC. That's going to be the important relation we have. So we have 100 kilograms of SiO2, and 100 kilograms is also 100 times 10 to the third, and that's included in that first term in the multiplication. Once we know the mass, we divide the mass by the molar mass of silicon dioxide. You would need to calculate this. That's the atomic mass of silicon plus twice the atomic mass of oxygen. In this case, that's 60.9 grams. So you take that ratio, and your product, or your final answer is 1,664 moles of SiO2. And if you have that many moles of SiO2, you expect to have the same number of moles of SiC because it's a 1-to-1 ratio. So our theoretical yield of silicon carbide is 1,664 moles. We can convert that into a mass by multiplying by the molar mass of silicon carbide, which is the sum of the silicon plus the carbon atomic masses. And then we divide that by 1,000 to get kilograms. And so this gives us 66.73 kilograms. That's the theoretical amount. So if we go back to our problem, we know that we produced 51.4 kilograms of silicon carbide was recovered. So now 51.4 divided by 66.73 times 100 gives us our percentage yield, which is 77%. It's shown here with 3 significant figures, which is correct based on all the information that we have. So at this point now, we've kind of gone through problem-solving strategies. It's important for you to do lots of problem-solving, to practice these strategies. If you have any questions on how to do this, please feel free to email or contact me by phone, and we can discuss problem-solving strategies to help you get to your endpoint.